What is up, everyone? Welcome back to another episode of the most missed OA questions. Today, we're going to be talking about the forces that hold the atom together. So those are going to be the strong nuclear force and the electrical force. And essentially what these do is they work together to make sure that an atom maintains its integrity, maintains its identity. And this is really important because atoms need to keep their identity. For instance, I'll give you an example. So, as you all probably know, carbon is an important atom in our bodies because all life that we know of is what we call carbon-based. Carbon is right here on the periodic table. If you look at the number in the top left-hand corner, this is called the atomic number. And the atomic number is essentially the identity of the atom. Because as you can see, each atom on the periodic table has its own unique atomic number. What this tells us is it tells us the number of protons that an atom has. So maintaining an identity of an atom is really important because if carbon has 6 protons, let's say that one day it was suddenly to gain a proton. So instead of having 6 protons, it has 7. If carbon were to suddenly gain a proton, it becomes nitrogen, which would be really bad for us because nitrogen is a gas. So that would mean that all of your carbon would turn into a gas and you would just evaporate. That would be a bummer. It would make reality very difficult to exist in. So as it turns out, there are a couple of forces that make sure that that doesn't happen, that makes sure that we don't suddenly turn into gas and float away. All right, so before we get too much more into that, let's talk about what an atom looks like and where the protons are in the first place, because obviously we're talking about protons. They're probably important here. Okay, so here we have an atom. And an atom is made up of protons, neutrons, and electrons. Pretty simple, right? I mean, it's only 3 pieces. Not a big deal. So the protons, and this is neutrons, pardon my really poor handwriting, that's supposed to say neutrons. Protons and neutrons are both found in the nucleus of the atom. So you may recognize this word from Unit 9 as well, because we use nucleus to also talk about cells. That's because nucleus is just a fancy word for center. So when you hear the word nucleus, atoms have a nucleus, it's the center of the atom. Cells have a nucleus as well. It's what the first scientist that looked at a cell under a microscope was like, oh, that looks like the center of the cell. I'm going to call it a nucleus. Okay, so protons and neutrons are in the nucleus, and that's this right here. So the protons and the neutrons are nestled in here. And let's draw the protons like this, and we'll draw the neutrons gray, and we'll draw the electrons yellow. The electrons are not in the nucleus, they are in the electron cloud, also known as shell. So you can call it the electron shell, electron cloud, whichever, doesn't matter. So they are going to be out here, and they basically just orbit the atom. So the electrons are all on the outside zipping around, and the protons and the neutrons are on the inside. So since we were talking about carbon, let's use carbon as our example here to describe the forces that keep carbon together so that it stays carbon. It doesn't change into something else. So again, I said carbon has 6 protons. So let's draw those. 1, 2, 3, 4, 5, 6. 6 protons, according to the periodic table, is carbon. If it has a different number of protons, it's something totally different. For instance, if it only had 5 protons, it would be boron. If it had 9 protons, it would be fluorine. Protons dictate the atom's identity. Okay, one more thing. Oops. in order to tell how many neutrons an atom has, it's really simple. So it's kind of hard to see, but right here, carbon has a number underneath the name. So I'm going to draw this for you a little bigger. So carbon looks something like this. So number 6, a big C for carbon, and then there's a 12 written underneath it. This number underneath is the mass number. So up top we have the atomic number, which tells us how many protons. And then underneath we have the mass number. It tells us how much the atom weighs. And the mass number tells us how many things are in the nucleus. So if the mass number is 12, and we have 6 protons, it's really simple. So 12 is the mass number, minus 6 protons, it tells us we have 6 neutrons. Because the mass number is always, always, always going to be the number of protons plus the number of neutrons. So 12 minus 6 equals 6. 6 plus 6 is 12. So carbon also has 6 neutrons. And neutrons are important. We'll talk about why here in a second. Okay, so here's our atom. We have the protons and the neutrons in the nucleus, nice and cozy, because that's where they like it. That's where they have to live. Now, the idea of the strong nuclear force and the electrical force this is what we're talking about here, the strong nuclear force and the electrical force, is to make sure that that atom maintains its identity. And again, an atom loses its identity, it changes identity when a proton is added or subtracted. And I'm going to tell you right now that that does not generally happen. It's not easy to put a proton in or to take a proton out. And here's why. Atoms are really, really, really good at maintaining their identity. And that's lucky for us because, again, if not, it would make reality very difficult to exist in. So these are the two forces that make sure that the atoms maintain their proton number. So let's start with the strong nuclear force. What is the strong nuclear force? Well, this one's actually really easy. It is a lot like an atom's own personal gravity. So the strong nuclear force pulls all of these guys towards the center of the nucleus. So the strong nuclear force is an attractive force. It pulls everything into the center. Again, it's like an atom's own personal gravity. It makes sure that everything stays nice and tight. So let me ask you this, because this is, again, for the most missed test questions, and this is the reason that people miss this question. If the strong nuclear force is just like gravity, can it ever repel? Does gravity ever push things away? It doesn't, right? You never experienced anti-gravity. It would be really cool if you could, to have some type of gravity that pushed things away, because then we could all hover around and have, flying cars that didn't use, didn't need like gasoline or some other type of fuel. They would just float. Anti-gravity does not exist. Therefore, gravity never pushes things away. The same thing with the strong nuclear force. And this is where people get tripped up. The strong nuclear force will never ever repel. It always attracts. It's like gravity. It's always pulling things towards the center. So the strong nuclear force is like gravity. It is an attractive force. Not in that it is attractive and that it's good looking. It's attractive in that it pulls everything towards the center. It is an attractive, not a repulsive, not a repelling. And that's it for the strong nuclear force. It's really easy. It just makes sure that all of those atoms stay nice and tight. So now let's talk about the electrical force. The electrical force you were actually introduced to in Unit 2 when we talked about Newton's equations for gravitational force and the electrical force. So the gravitational force equation looks something like this. You've got constant multiplied by mass of object 1 multiplies the mass of object 2 over distance squared. We're not talking about that right now, so just forget about it. The electrical force was similar. K times the charge of object 1 multiply the charge of object 2 over distance squared. We're not talking about this equation either. I just wanted to let you guys know that this is all part of Unit 2, and it's also another test question. I cover it in one of my earlier videos. You can see it in the same document that you found this video. But there is an underlying principle here that's really important. The electrical force talks about this invisible force that causes things to be pulled together or pushed apart depending on their charge. So when we talk about charge, we're not talking about like your toothbrush is dead, so it needs to be charged up. We're talking about something else. We're talking about a different kind of charge. We're talking about the charge that, what's the word I'm looking for, that an atom can have, that a particle can have. So lots of things can have charges. A really great example is sodium chloride, which is also known as table salt. The reason that sodium chloride exists is because sodium has a positive charge, and chlorine has a negative charge. So what do you guys know about opposites? Opposites attract, right? So sodium and chlorine love each other because they have opposite charges. They like to stick together like little magnets. In fact, the electrical force is very, very similar to magnetism. Because if you have a magnet with a north and a south end, and you put it together with another magnet like this, the opposites attract. So north and south are going to want to stick together. What about if you change one of these magnets around? So you have north and south here, and then you have south and north here. Do the south side of a magnet and the south side of the other magnet, do they like each other? They really don't, do they? They hate each other. They will repel because opposites attract, like repels. So let's look at this in terms of sodium. Given what I just said, if we have a sodium molecule atom next to another sodium atom, what are they going to do? They are not going to stick together. They are going to push away from each other because like charges will repel each other. Opposites attract, the same repels. Same thing with chlorine. If we put two chlorine atoms next to each other, they both have a negative charge, so they are going to repel each other. Okay, I think that's probably pretty clear at this point. Opposites attract, like charges repel each other. So let's go back here to our picture of our atom. Okay, you know what? That's actually a little busy. Maybe let's draw a new one really quick. I'll make it a bit easier to follow if I draw a clean picture. Okay, so again, our three parts are protons, our neutrons, and our electrons. Here is our nucleus. Protons we're going to draw with this color. So again, we're going to go 1, 2, 3, 4, 5, 6. Neutrons we're going to draw with this color. So we've got 1, 2, 3, 4, 5, 6, just like before. And then electrons, we draw with this color, so of course they're out here. All right. Some of these parts of the atom have what we call a charge. Just like sodium has a positive charge, protons have a positive charge as well. Just like chlorine has a negative charge, all electrons have a negative charge as well. Now you might think that protons and electrons would be attracted to each other. Yes, under normal circumstances, if they ever got close enough together, they would be. But that never happens. It almost never happens. Not that you have to worry about in this class. You don't ever have to worry about protons and electrons being near each other because it just doesn't happen very often. So don't worry about those attracting each other. You will not be asked a question on the exam about that. Instead, what you're going to be asked about is how the electrical force helps keep this atom together. Because remember, the strong nuclear force pulls everything in. The electrical force, on the other hand, is going to do something else. So the strong nuclear force keeps all the protons inside of the nucleus. That means that our carbon atom here is not going to lose any protons to become boron or become beryllium or lithium, because the strong nuclear force is going to keep all of those protons nice and tight tucked inside of there. The electrical force, then, you can probably guess, is going to keep things out. So the strong nuclear force keeps things in. The electrical force is actually going to keep things out. And here's why. Imagine if you have a proton, and he's sniffing around here. He's like, hey, that looks comfy. Well, he's got a positive charge. And so does this guy. So when he gets close to this guy, what's going to happen? He's going to be repelled. The electrical force is going to repel him. He's not going to be able to get into the nucleus because that electrical force is going to be like, get out of here. And it's going to knock him out. So the electrical force does a great job of keeping other protons out of the nucleus. And that's really it. That is it in a nutshell. The strong nuclear force keeps things in because it is an attractive force. It is like gravity. The electrical force keeps protons out because protons all have a positive charge, and like does not like each other. They're going to repel. So let me ask you about this really quick. So I told you the strong nuclear force is like gravity. What happens to gravity if something gets bigger? If you increase the mass of something, what happens to the gravity? Just think about it for a second. The answer is it gets bigger as well. If something gets bigger, its gravity increases as well. Think about you. What would happen if you were to suddenly gain like 100 pounds? You feel a lot heavier, right? Your gravity would increase. That's why, so like Earth, we live on it. Earth's pretty big. I'll go ahead and draw that really quick. So Earth is like this size, and we'll say the moon is like this size. So we live on Earth, so we know that it has gravity. But what about the moon? What about that time that Neil Armstrong went to the moon and he did his famous moonwalk? He was able to jump like 20 feet in the air, which is something we could not do here on Earth. That's because the moon is so small. When something gets smaller, it has less gravity. What about when something gets bigger? Like, let's look at the sun. So the sun is massive. It is thousands and thousands and thousands and thousands of times larger than Earth. Because it's larger, it has a lot more gravity. So if you were to be able to go to the sun and not be burned up, the gravity is so intense it would crush your whole body to the size of a marble. I mean, that's how intense the gravity is. Because the sun is huge, the bigger something is, the more gravity it has. So let me ask you this question about atoms. So what do you think would happen to the strong nuclear force if you were to start to pack in, and I know you can't do this, so this isn't a possibility, but let's just pretend that it is. What if you were to start packing in more protons and more neutrons? If you were to make this atom bigger, what would happen to the strong nuclear force? It would get bigger as well. Okay? The larger something is, the more gravity it has. The strong nuclear force is just like gravity. So the larger the atom is, the more gravity it's going to have. Okay. So then, what would happen if you were to make the atom smaller? You probably guess the strong nuclear force is going to go down. Again, we already talked about that. Okay, what about, let's talk about the electrical force. What do you think happens when you start to get to the electrical force, when you start to inch these protons closer and closer together? So as this positive charge and this positive charge, as they get closer and closer together, what happens to the electrical force? It gets bigger. So think about this. If you have two magnets and you're holding the north end towards the north end, if you get right here, you probably can't feel anything. But the closer you get, the more you feel it's pushing back and it's pushing back, and you try and push them together, but you can't. It's because the closer you get those together, the stronger that force becomes. The more you pull them apart, you suddenly can't feel it anymore because it's so weak, it's virtually non-existent. But the closer you get those, the more you got to fight it because they just don't want to touch each other. So the stronger, or the closer two charged particles get together, the stronger the electrical force becomes. The further apart they get, the weaker it becomes. Those are the main concepts that you'll need to understand in order to answer the questions on the test. But as you can see, they're actually really straightforward. The vernacular and the way that they're described in the material can make it confusing, but they are really that simple. If you have any questions, feel free to email me at any time, or your course instructor, or go ahead and reach out to me by phone. There's my extension. Anything you guys need, if there's anything in here that needs to be cleared up or that wasn't explained well, let me know, because then I can come in and I can make edits to the video. Otherwise, thanks for watching and good luck on the test.